Yeah. So this is going to be, I think, the true benefit to doing the live stream is everybody can ask homework questions now. Like they can type up homework questions in chat, and you guys get to ask them live, and everybody gets to see them worked out, which hopefully will cut down the amount of time I have to spend doing them when you guys show up on Monday, when they show up on, or when you guys show up on Thursdays and they show up on Mondays.
At 8:12, maybe sure. Oh, it's today.
I should also let you guys know that Mrs. Reed might be stopping by because she's taking a personal interest in what we're doing here. Because she wants to find the best way to help all of our students. So she has a number of teachers trying different things out here. Hi, Todd. Hi, Michaela, Caleb, Allie, Anne-Marie. Hope we're all doing well. Guys, I'm going to give a chance for you all to ask homework questions too. So if you have any homework problems, you can go ahead and type them up in chat, and we'll go ahead and we'll do those ones too. Hey, Luke, how's it going? Thank you, appreciate it.
No problem, no problem. Brighter
I got my Hollywood setup in here going. You guys that are physically here, let's get our homework out so that way I can check quickly and we'll get on our way.
Are we doing any questions from it or no?
Sorry?
Are we doing any questions from homework or no?
Absolutely we are. Not only are we going to do your questions, but hopefully if anybody in chat has questions, we can tackle those too.
Oh. Well, I was really confused. You said -2 and I was like, but I did all of them.
That's the easiest handwriting I think I've ever seen in my life. I'm impressed.
That was the thought, even mine is the pretty.
I've seen worse. Every day when I write.
Sausage was going all over.
All right.
Was it parents performance?
All right, gang. Let's go ahead and just get this show on the road. So if we have homework questions from 3.1, we'll go ahead and we'll knock those out. If anybody in our live chat there has homework questions, we'll take those too. Though I also understand that maybe since you know I'm not checking yours till Monday, if you didn't actually start the homework yet, you wouldn't have any homework questions. But are there any problems from 3.1 we'd like to talk about, we'd like to go over or go through? Allie?
13 and 25.
13 and 25. 13, 25. What else?
29.
29. Team, is that 29? I have adjusted our live stream, by the way. It's no longer a public live stream. You have to have my link in order to be able to join it. That way, if anybody don't want to be out there on the internet, well, you're not. So, Mr. Kaufman definitely ain't making 1 million subscribers, okay? All right. DJ, you let me know if anybody in chat pops up with a question, okay?
Yes, sir.
All right. Let's go ahead. Let's talk 3.1. Let's go tackle these problems here. Let's tackle these homework problems. Let's start here with number 13. Number 13, what do we got for, we got find any critical numbers for this expression. We got g of t. And we got that as t square root 4 minus t. And we are looking specifically at t values that are less than 3. That are less than 3. Okay, so how are we going to find some critical values here? What do we need to do? We need to get a derivative going, right? That's what we did yesterday, and then we'll go ahead, we'll find the zeros for it, correct? Now, when I look at this thing, this is going to be, I'm going to need to rewrite it. I'm going to rewrite it as t, and then I have 4 minus t to the 1/2. So when I look at this, when I go to start doing this derivative, this is going to be a product rule. It's going to be a product rule, f and g. So I'm going to g times f derivative, g derivative, f. Okay, well, let's just go ahead, let's write this out. F derivative here is going to be 1, so that should be easy enough to do. G derivative here is going to be 1 over 2 root 4 minus t. Thank you, Ms. Underwood, appreciate you. Okay, now all we need to do is just plug everything in where it needs to go and multiply down. So g here is square root 4 minus t. And of course, that's going to be times 1. And then we're going to have our 1 over 2 square root 4 minus t times f, which is, of course, just t. So what do we have here? We have 4 minus t plus t over 2 square root 4 minus t. I think the best thing to do here is, because eventually we are going to want to put this to 0, is to go ahead and try to combine this into one cohesive fraction. So let's multiply the top. Yes.
Hey, is there any way that I could see Callie Payne in Coach Resendez's office very briefly?
Yes, sir. So let's multiply the top and the bottom by our common denominator here, which is 2 square root 4 minus t. 2, 4 minus t. So what this is going to do for our numerator here is going to unlock 4 minus t plus t all over 2 square root 4 minus t. Now it just comes a little bit of simplifying, just a little bit of more work here to simplify this down. Send your 2 in, combine your like terms. We're looking at 8 minus t all over 2 square root 4 minus t. Are we all okay here? This is our finalized derivative. This is where most of the work is taking place for this problem. It's just getting to this derivative. It's really no different than what we did in the last section, last unit, what you did on your last test. And in fact, this is very similar to one of your problems from there. Are we okay with what I've done? Bianca, question.
Wait, okay, so whenever I took the derivative of the square root of 4 minus t,
Yes.
I actually used the chain rule to do that, and I got that.
There should be a negative there.
Yeah.
Yep. Good catch. That's a negative, 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 and that makes this 3t minus 3t. So when we send our 2, 4, we get 8 minus 2 minus 3t. Yes, good catch there. Good catch. It is easy to make a little mistake, but Mr. Kaufman does it often. So now we are going to take this and we're going to talk about the two situations for critical numbers, which are what? When we're equal 0 and when we are undefined, right? Okay, so when we equal 0 is going to be pretty easy. 8 minus 3t equals 0. This is, of course, where our derivative of x is going to be equal to 0. And this is going to give us t equal to 8 thirds. 8 thirds. We can subtract the 8 over. We'll divide by negative 3. Negative 8 divided by negative 3 gives us positive 8 thirds. We all okay with that work? Okay. Now, we do also have a situation where this will be also undefined or does not exist. And that's going to be where our denominator equals 0. More specifically, where 4 minus t equals 0. And 4 minus t equals 0 at t equal to 4. Do I need to worry about this situation, though? No, it's not in my description. When we started this, we said right here, t has to be less than 3. So t cannot be 4. So this one does not exist for us in our interval. So this is the only critical value we need to be concerned about is 8 thirds. Questions here? It doesn't ask me to find the extreme, so I don't. I could. Let's take a look at 25 and 29. 25 and 29. For number 25, we are going to locate the absolute extremes on this closed interval. So very much like we did at the end of class yesterday, looking at 25, we have g of t is equal to, we have t squared on the top over t squared plus 3 on the bottom. We do also have the interval here of -1 to 1. -1 to 1 with brackets. Okay, so of course we're going to go ahead. We are going to start by getting the derivative. This is going to be a good little quotient rule here for us, fg. And f prime is going to be 2t. G prime is also actually 2t. So we have the same derivative there for both of those, which is convenient. So when we set up our g derivative, we have g f derivative minus f g derivative all over g squared. So this is going to be 2t squared plus 3 times 2t minus 2t times t squared. All this over t squared plus 3 quantity squared. Are we okay with what we've set up so far? Comfortable? Yes? Okay. Now we just need to go ahead and do a little simplifying here. Let's do a little multiplying across the top here. I'm going to get 2t to the third plus 6t minus 2t to the third all over. I'm just going to continue to leave this denominator unexpanded. I can cancel my cubic functions on the top, and that leaves me with just a 6t over t squared plus 3 quantity squared. Are we all comfortable here for our derivative? Okay. Now we already have some numbers we need to test. We need to test -1 and 1 because those are our endpoints here. So when we're looking at g of -1, g of +1, let's see if we have any critical numbers here. Is there any point where this derivative is going to be undefined, does not exist? I don't think so. We would need t squared plus 3 to go to 0, and that's only going to happen if we bring in imaginary and complex numbers. I don't think you guys want to do imaginary and complex numbers with calculus, do you? Yeah, even in my time doing my mathematics degree, I never did calculus with complex and imaginary numbers. That's like doctoral level math. If you're doing that, you're getting a PhD in math, and I hope that you go work for MIT. So we're going to focus on when this is going to be equal to 0, which of course is when t is 0, yes? So we have g of 0 that we need to plug in as well. These are our three values we are going to test. We're going back to the original function here, which should be pretty easy. -1 going in is going to give us 1/4. 1 going in is also going to be 1/4. And 0 going in is in fact 0. These are the values we are looking at here. So I have an absolute max here. I have an absolute min here. Questions here, concerns here about this one?
So do we just put both of those points as the absolute maximums, or do we just put 1/4?
I would just put the absolute maximum is 1/4.
Okay.
Because that's what it's asking me to identify here. It says locate the absolute extremes. So it's asking what is the maximum, not where is the maximum. And because it's the same value, it can occur twice. We can reach the max more than one time so long as it's the same max, right?
Mm-hmm.
The way I like to equate that is for those of us that do any type of like weight training or anything like that, you have a max rep weight that you can do. You can do maybe 2 or 3 at that weight for whatever you might be doing. So you can hit that 2 or 3 times, but that's the max. Anything over that, you have trouble getting even just 1. Does that make sense? Okay. And number 29 is relatively the same thing, except for it has absolute values, which I now recall that we did not actually talk about doing derivatives of absolute values, so I see the issues there. That's on me, and I will get back to us all on that. I'll probably make a brief little video on how to do derivatives of absolute values. So that's my fault. Forgot, I just, it just got past me, I guess. Questions here? We'll come back to that one later on. All right, today we are going to go ahead. We are going to do 3.2. We are going to talk Rolle's theorem and the mean value theorem. Rolle's theorem and the mean value theorem. These are extensions of finding the critical numbers and doing the extremes that we talked about yesterday. This is an extension. This is continuing on from where we left off yesterday. I need to get my keyboard. So let's go into the first slide here, past the title slide. So Rolle's theorem, I know it's cut off a little bit there at the top. Rolle's theorem is that we need a continuous function f on a closed interval between a to b, just as we've talked about before. It needs to be differentiable on this interval from a to b. Now, when it's differentiable there, it doesn't have to be differentiable at the actual endpoints of your interval, because it technically can't be, because you don't know what's on the other side of A, you don't know what's on the other side of B. So it won't be differentiable at those points itself, but leading up to, it should be. So if your function is continuous and differentiable between these 2 points, between your low point and your high point, if they actually end up being the same value, if A and B spit out the same y value, if your beginning point matches the same y value as your end point, then somewhere between the two, you have a critical value. Somewhere between the two, you have a critical value. That is what Rolle's theorem is telling you, is if your function is continuous and differentiable on an interval, and if the interval begins and ends at the same y value, then somewhere in that interval, there is either a maximum or a minimum for you to deal with. There is at least one critical number. You can see how this is an extension of what we did yesterday, because if you don't know how to find a critical number like we did yesterday, and as we just reviewed, then you wouldn't have no idea what I'm talking about now. So this is taking what we did yesterday and taking it one step farther. Now I can guarantee you that there will be or there won't be one in this interval. Rather than doing what we just did, for number 25 or for number 13 from homework, the two we did, which was, do we have it? Let's find it if we have them. Now I can say definitively there will be one or there may not be one. So if I looked at 25, which I think is a really great example of this, 25 that I just did, I can't remember which one you guys asked me for, but it's awesome that you did. 25 began at -1 and ended with 1/4. And it had 1 as the other endpoint, and it spit out 1/4. And that was Bianca's question, right? So we would know by Rolle's theorem that somewhere between the two, there is a critical value. And there was, wasn't there? Between -1 and 1, we had the critical value of 0, which ended up being our minimum. So this is how we're going to use this. Now, we're going to work through a couple of basic problems. The first thing we have to do is we have to verify that Rolle's theorem even applies. Okay? Questions here. What I have popping up there in white is what I'm trying to say. I feel like that's the best way that I can tell you to copy down what you need to know about Rolle's theorem is there, what I have in white. That's my rewrite of it, is if f of a and f of b are equal, then there's some c between the two where c is a critical value. This is only true if the function is continuous and differentiable in this interval, though. So that is the caveat here. So this is a visual representation of what we are talking about on the next slide, this graph that looks kind of like a sine graph. Is if I know that between A and B, I know my function is continuous, I know it's differentiable, then therefore, it has to be moving up and down. There's no breaks, no gaps, no jumps. Which means at some point there's going to be either a peak or a valley, possibly both, before we come back to neutral, before we come back to that starting level. Does that make sense? And there might be somebody out there saying, well, what about if it's just a straight horizontal line all the way across? And that f of a is the same as f of b because they're all going to be the same. Okay, well then great. We still have a maximum minimum. We still have an extreme situation, don't we? Questions here? Okay then. So let's just take a look at our first problem here, problem number 1, our x squared minus 5x plus 4. And let's just look and see, will this theorem apply to this problem? Will this theorem apply to this problem? So, what type of graph is number 1? What type of function is this?
Quadratic.
It's a quadratic. Now, you know parabolas well. Do parabolas have any vertical asymptotes we need to be aware of? Do they have any breaks in the graph that we need to be aware of? No. A standard quadratic exists everywhere. It is a smooth, continuous function, right? Thus, it should be a smooth, differentiable function as well. So, is the function continuous between 1 and 4? Yes, it is. It's a parabola. We know this well. Of course, we could use Desmos, or we could test this other ways. I recommend graphing it. That's probably the easiest way in Desmos. And then, okay, is the function differentiable between 1 and 4? Once again, yes, it is. Yes, it is. Okay. Well, then, what we'll do here is we'll test 1 and 4. That's the next part, right? We've tested it that it's continuous. We tested that it's differentiable. So we need the endpoints to have the same y value. So when I plug in 1, when I plug in 4, do I get the same y value? When I plug in 1, when I plug in 4, do I get the same y value? Let's find out. We'll do it real quick. 1 squared minus 5 times 1 plus 4. This is going to give us 0. Yes? Okay. 4 squared going in. 4 minus 5 times 4 plus 4. This is also going to give us 0, right? So it looks like Rolle's theorem will apply. So there is some critical value between 1 and 4. Are we all okay with this? So since the two y values match, there is some c value between these two. If we want to find that, how would we find this c value? The second part here is find any c values that would work, right? Okay, well, how do we do that? What do we do for number 13? What do we do for number 25? We do the derivative. We do the derivative. Now, we are only looking for critical values here, so we're not going to test the endpoints this time. Plus, we already did. They're zeros. Both of them are zeros. So when I do the derivative here of x squared minus 5x and plus 4, the first derivative of f is going to give us 2x minus 5, which will set that equal to 0, and solve, and I've got x equal to 5 over 2, or 2.5, which is in fact between 1 and 4. Are we all okay here? We're all comfortable here. Does chat have any questions for us? Anybody at home? Okay then, let's go ahead, let's move on. So, what about this one, number 2? Same direction for number 2? What do we think? Let's use common sense here to help us with this. Well, of course, we can graph it if we want, but let's try to use some common sense if we can. What type of function is number 2? What's its parent value? It's an absolute value graph. Now, you know that those are continuous, right? There's no break in an absolute value graph. There's no vertical asymptotes that we need to worry about. So it will be continuous, right? Will it be differentiable? Not everywhere. So we have to pay close attention to our interval here. Absolute value graphs have a sharp point at 0, right? So if our interval involves 0 or goes over 0, like between -1 to +1, which has 0 in between, then it's not differentiable on the interval. Look at my interval here. It's 0 to 6. Will it be differentiable then? So we established that it's continuous. This next question is it differentiable? It's yes or no. What do we think? Jake says no. He is correct. It's not differentiable at 0. It's the problem. That's the issue. The theorem doesn't apply. We're done.
Isn't that 3?
Pardon?
Wouldn't it be like moved over 3?
Yes, but 3 is going to be our new vertex, Jake.
Yeah.
So yes, you're. Let's be clear. It's a good question. It's a good question. So when I'm saying 0, I mean the 0 of the function y equals 0. At y equals 0 is where we're going to hit that vertical asymptote, traditionally on a parent function of the absolute value. Now, Jake's on to something here because, of course, as we've all talked about in Math 2, this has been transformed. It's up 3, reflected x-axis, and then right 3. So technically, the vertex for this graph would be at 3 for the x value, which is smack in the middle of our interval, which is why it is not differentiable. So let's not be confused here. It's not because 0 is in the interval. It's because the 0 of the function is in the interval. The vertex of this function is in the interval. Does that make more sense? Let's focus on that. At the vertex of an absolute value, we have a sharp point, which makes it undifferentiable. The vertex of this graph is in this interval, and therefore we can't do the derivative there. Does that make better sense? Better terminology. Jake, thanks for helping me out with that one. That's a much better way to explain it. You got to remember, this is only Mr. Kaufman's second rodeo with calculus, so I'm still trying to figure out the best way to explain everything. It's not exactly like this. This is an easy topic to run through like it is in Math 2. Okay, let's move on to this one. Let's move on to this one. We have a nice rational function, x squared minus 1 over x. X squared minus 1 over x. Okay, now this is a rational. Now we know rationals have lots of asymptotes involved, right?
I'm so sorry.
It's okay. We know with this one here, there's lots of asymptotes involved. Is there going to be an issue here with an asymptote on my interval? Between -1 and 1, looking at this function, are we going to have an issue with some asymptotes? I think so. This will have a vertical asymptote at x equals 0, which is in the interval. So this is not continuous everywhere. Therefore, it's not differentiable everywhere, and the theorem does not apply. Questions? Concerns? So I wanted to make sure we looked at a few where you don't have to do anything more other than prove to me that it's either not continuous everywhere or it's not differentiable everywhere, and then we can be done. I do want to go back to the very first one we did, like problem number 1, where it should work, it will work, and we can go all the way through it just to make sure. Okay? Does that make sense? Just to make sure we're all on the same page before we move on to mean value theory. I don't think Rolle's is very difficult because it's really just extending what we did yesterday with more specific starting information. Let's call it that. So, going back to the original instructions, does Rolle's theorem apply here? And will it, in fact, if it applies, can we, in fact, find that C value? So, I have here a new function for us. Now, I updated these slides a little bit ago, so some of these problems might not have fully updated in Canvas yet. So I'm going to make sure I write it out here. We have f of x equal to, we got x squared minus 2x and minus 8. And Mr. Kaufman forgot to put the interval up here. Give me 1 second to think about what the interval is supposed to be. Let me go double check. I have it written down over here. The interval here is -1 to 3. -1 to 3. -1 to 3. Okay, now I've talked my way through the last couple of problems, so I would like somebody to help us out here. If you don't want to be heard on the live stream, that's fine. Just don't talk too loud. Who wants to help out?
I will.
Maddie, you gonna help us, okay? So Maddie, let's start with, is it continuous?
Yes.
Yes, it's a parabola. We know parabolas are very well known for their continuous, okay? Is it gonna be differentiable everywhere? Yes, no sharp points, no breaks in graph, right? Okay, so let's test the endpoints. The endpoints have to have the same y value here, correct? Okay, so when I test the endpoints, f of -1, well, that's gonna be -1 squared minus 2 times -1 minus 8. What's that going to give us?
-10.
Try again.
-6.
-5.
-5. Sorry.
It's okay. All right, let's check the other one here. F of 3. So 3 squared. 2 times 3 minus 8. 9 minus 6 minus 8. -5 again. So yes, in fact, Rolle's theorem does apply here. It's continuous, it's differentiable, and what's more is the endpoints line up. Can everybody on live stream see this? Let us know. Make sure that you can see this paint here. Yesterday it worked out okay, but I just want to make sure because sometimes it gets too faint to see as the marker dies. Are we all set here in person? Okay, so then let's find this critical value that's between 1 and 3. Negative 1 and 3. So Maddie, what are we going to do next? Derivative. What is the derivative here?
2x minus 2.
2x minus 2. What are we going to do with this? Set it equal to 0. I got 2x. I got x equal to 1. Is that what you got? Sounds good to me. Sounds good to me. You can plug it in to see for yourself whether this is going to be a maximum or a minimum. If it's going to be a maximum, it should be over -5. If it's going to be a minimum, it should be under -5. Does that make sense? It can't be the max and then the endpoints be higher than it. It can't be a min and then the endpoints be lower than it. That breaks the definition of literally being a max or literally being a minimum. Questions here? Like I said, I don't think rolls is too outlandish here. I don't think rolls is too outlandish here. It's just a few things we got to check before we do what we did yesterday. What about this one here? I did it again. I forgot the interval again. Hold on. To be completely candid, these aren't my problems. I'm actually stealing them from Miss Willis. She teaches calculus now over at CPCC. We're doing -2 to 1 here for this next one. -2 to 1. So our next problem here, the interval -2 through 1. And we have the function here. We have -x cubed minus x squared and plus 2x. Go ahead and try this one here without me real quick while we see if live stream has any questions. And then they can go ahead and catch up to us a little bit. How is everybody doing on the live stream? Are we doing okay? Any questions so far, DJ?
No further.
No. What are we talking about in chat?
Nothing really.
Nothing.
Nobody asked a question yet.
Maybe I should start doing all the standard YouTube streamer stuff. Like, make sure you're on the lookout for my new YouTubes, or like, comment, subscribe. Let me know in the comments what videos you wanted me to do next.
Caleb said he's doing good.
Maybe this be the part where I talk about my sponsors. This video was sponsored by Mr. Kaufman's Failing Sanity.
Oh, Parker said that the comments are restricted on their accounts.
Yeah, I know.
School accounts.
I know. That's why they can't comment. That's why I tell them to put it in chat, because they can't in chat. They can't in the comments. All right, let's go ahead. Let's start talking about this one a little bit. So you guys are still working here in class, but we can talk through a few first things. We have a cubic function here, right? Standard cubic function. Cubic functions, any asymptotes we need to worry about on them? Any issues that we need to talk about with a cubic function? I don't think so. There's no asymptotes for a cubic function. Any breaks in those? No, so it should be continuous everywhere, right? Okay, let's talk about, is it differentiable everywhere? Any sharp points that we need to worry about? The only times that we have differentiation problems are when we have continuity problems, which we already answered, there's none of those, or at sharp pointed graph, which we don't have with the cubic function, does curve nicely there through the middle. So the next step here is to test the endpoints. Do the endpoints match for us? Yeah? What were they? 0. When I put in -2, I get back. So I get -4. This is going to end up being positive 16, correct? No, there's no 2 there. Positive 8, sorry. And this is going to be our -4, yes. All that goes to 0. And 1 going in is pretty easy because then it's just going to be -1 plus 2. And of course, that all goes to 0 as well. So Rolle's theorem does apply here. Questions? How are we going to do Rolle's theorem? Maddie did the last one. Come on, somebody else. Abby, what are we going to do next? Find the derivative. Okay, what is the derivative, Abby? -3x squared minus 2x plus 2. Okay, now what? Set it to 0, right? Okay, how do we solve something like this? How are we going to find our zeros here? What's the first thing you're going to try? Factoring, did it work? Nope. What's our backup plan? The good old friend, -b plus minus square root b squared minus 4ac all over 2a. Oh, I'm so excited. So excited we're bringing back our Math 2 problems. You saw me do factoring yesterday. You think you were going to get out of here without having to do at least one quadratic formula problem? Come on now. 2 plus minus 4 minus 4 times -6. And that's all going to be over 2 times and all over -6. We're looking at 2 plus minus square root of 28 all over -6. It's going to be 2 plus minus 2 root 7 all over -6. We can go ahead and drop some 2's out of here. I got 1 plus minus square root 7 all over -3. Now, when you do all that, when you punch it all in, does both of them work? This is technically 2 answers here. Those are technically 2 answers here. There is 1 plus square root 7, and there's 1 minus square root 7. Grab a calculator. I got one down here. When I do 1 minus square root 7 divided by -3, I get 0.5485. So that is in my interval. That one's okay. When I go the other way, I take 1 plus square root 7 divided by -3, I get -1.21. That one's also in my interval, so both here are in fact okay. We have 2 critical values. Remember, Rolle's theorem specifies that there's at least 1. It didn't say there couldn't be more than 1. There's actually 2 here. Questions for this one? I think you can see why I made sure I wanted to get through a few more of these. It can be a little bit trickier. Okay, let's move on to the mean value theorem, aka how we are going to start approaching average rate of change. How do we mix slope back into all of this fun stuff we're talking about today? So First, I have a question for you. I want you to try to sketch a graph that has these properties to it. I want you to try to sketch a graph that has these properties to it. As we're doing this, everybody's graph should be different. This is something that we need to talk about, and while I have you all here and some of you on live stream, I'll go ahead and tell you all, flat out. Questions like this really show and tell who's doing their work and who's relying too much on each other to help with their work. And we are getting dangerously close. I want to make sure I got your attention. We're getting dangerously close to ending up like AP Stats again, where we have crossed the line and now we're cheating. We're getting too close to that line. You need to be more responsible for what is your work and your work alone. I don't mind if you ask each other questions, but when we have the same wrong answer with the same wrong steps for the same question, that is oddly suspicious. Especially when there's only 2 or 3 people that made that mistake. It makes those 2 or 3 people look like they worked a little too much together. We're getting too close to that. I don't mind you guys helping each other out, but rather than turning to each other and asking questions, the first person you should turn to ask a question is me. Okay? I don't want to have to do what I did in stats. So let's reel that back in a little bit. Okay? So when I look at this graph, we can have just about anything that we want here for this. We have a couple of things we need to match here. We need 1 to have a y value of 3. We need 5 to have a y value of 6. 1, 2, 3, 4, 5. And we want this to be differentiable between the 2 points. So really, it needs to be continuous. It's a nice smooth line. And no sharp points. So outside of that, we can do whatever we'd like here. We can do a couple of things like that. Get a couple of maximums and minimums involved. We could just have one dip. You can just draw a straight line. All of those will work. Questions here? So what we're going to talk about is what is the mean value through this type of picture. What would be the average slope through something like that? Where all of them are going to be different, but they all have the same common feature. They all have the same end point, begin point, and they're all differentiable. How do we find the average, the mean value throughout this? And that's the mean value theorem. So it works very similar to roles, which is why they always go together. The criteria here is the same. It needs to be continuous. It needs to be differentiable, which is the same 2 things as Rolle's theorem needed. However, the last part of it is a little bit different. We're not going to test the endpoints to be the same. We don't need the endpoints to be the same here. What we're going to say is if it's continuous and if it's differentiable, then there's some C value between the beginning and end of our interval that will give us the average slope. There is some value that will be the average slope between these 2 parts. And that's what you see in the formula there. That's what you see in the formula there. On the left side, you have the derivative with C, which would be the slope at the point C. On the right side, you see the standard slope formula, y2 minus y1 over x2 minus x1. So what we're saying here is that somewhere throughout A to B, there's a value that has specifically the exact average of all the slopes together there. We call this the idea of doing a secant. And yes, this is the same secant from trig. This is how trig actually got started. Remember back in pre-calc, I told you the true original trig functions are not sine, cosine, tangent. It's sine, tangent, and secant, because they spawned out of calculus. Trig was after calc, not before. We've already talked about sine graphs, which are wavelengths graphs. Tangent lines are derivatives. We've talked about those so far. And now you know what a secant actually is. A secant is the average slope, the average rate of change between these 2 points, between a curved graph. So now I've taught you calc and a little bit of trig at the same time. Questions here? Okay. Given that I have f of x with 5 minus 4 over x, going on to our first problem, I want to find all the values of c between 1 and 4 that will make this true. So, given this information, let's apply our mean value theorem. So for the first things for our mean value theorem, we need to be continuous and differentiable on our interval. Are we continuous and differentiable on this interval? Is there any number between 1 and 4 that I need to be concerned about plugging into my equation? No. Yes, there will be a vertical asymptote for this graph, but it happens at 0, which is not in my interval, so I don't care. So between 1 and 4, everything should be fine. It is continuous, and it should be differentiable. So from here, we need to get ready to use our formula. So we have A as 1. We have B as 4. We need F of A, which is going to be, of course, 1. When I plug 1 back in, I get 5 minus 4, which is 1. And then we have to get F of B, which, of course, is going to be when I plug in, of course, 4 itself, which is going to be 5 minus 4 over 4, which is 5 minus 1, which gives us, well, we'll hold 4 again. So we got 1 and 4 and 1 and 4, right? Is everybody okay with the first 2 steps? That's what I've done. The first 2 steps there in white is I've just flushed out some of my beginning information. Okay. Well then, let's plug it into the formula and let's see what happens here. So on the top here, we're going to have f of b minus f of a. That looks like 9, f of a. Over b minus a, so that's going to be 4 minus 1, 1, which gives us 3 over 3, which is 1. Gives us 1. Are we okay with this? Are we all comfortable here? Okay, so the average slope for this graph between 1 and 4 is the slope of 1. An increasing slope of 1. Are we all set here? Okay. The next step of this will inevitably be to find what C value spits this out. What C value is going to spit this out? We already have it. I don't need to do it again. If I do the derivative, set the derivative equal to 1, I'm going to find this value all over again. Questions here? Concerns here?
So you don't have to take the derivative?
Well, let's do it. Let's take the derivative. The derivative here of 5 minus 4 over x squared. First, let's rewrite this for f of x. This is going to be f of x 5 minus 4x to the negative second, correct?
That's not x squared, is it?
No, it's just x, sorry. Just x to the negative 1, x to the negative 1. So when I take the derivative of x, we're going to go ahead, we're going to get, that's going to go away. And this is going to become positive 4 and x to the negative second, which is where I got ahead of myself. So what are we going to do with this? What are we going to set this equal to? We're going to set it equal to R1. 1 equal to 4 over x squared. That's what we're looking at, correct? Okay? Solve it out. Plus and minus 2. Are we okay with how I solved it out? Okay. Now only one of these c values are in my interval here. So I'm not going to keep negative 2 because negative 2 is not actually in my interval 2. X equal 2 is where this average slope is going to take place. That's the value that's going to spit this out. That's the critical, I shouldn't say critical because that makes it sound like it's a tree. That's the important value here that we're at. Questions? Concerns? Okay. Let's try another one. Let's try another one. So what do we have here? We have f of x. We've got negative x cubed. Is that plus our x squared, right? And plus 2x at the end, correct? Okay. The interval that we're worried about here is negative 1 to 2. Negative 1 through 2. Okay, what's the first thing we're going to do, gang? You just watched me do 1. What are we going to do now? What should we check first? Continuity, differentiability, right? Is this continuous? Yeah, it's a cubic function. No issues to be worried about. Second, differentiability. Since there's no continuity errors, is there any sharp points that I need to be worried about with a cubic function? Not traditionally. I'd have to work pretty hard to make there be one. So, checks meet. What do we need? What are we going to start building?
Plug in your A and B.
We need to get some values, right? We have to get our A and B going here. A here is, of course, negative 1. B here is, of course, going to be 2. So what is f of A? When we plug in negative 1, what's going to happen? It's going to be what? 0? Negative 1 going in, that's actually going to end up as a positive 1 because there's 4 negatives involved there. Plus 1, that gives me 2, but that's going to nullify those. So yes, 0. What about when I plug in B? What's the f value of B here? Callie says it's 0 again. We're going to get negative 8 plus 4 plus 4 more. I think it's also 0. Questions here so far? Okay. So, we've answered the first 2 questions. Is the function continuous? Yes, it was. Is it differentiable? Yes, it was. Then the theorem can be applied. So, we need to get our derivative as well, too. So, let's get that out here. Our derivative here, our f prime. First derivative of x. Negative 3x squared plus 2x plus 2, correct? Okay? We're going to take this, we're going to set it equal to what comes out here. Now you can either do this in one full step. This is completely up to you. Completely up to you. Last time I did it two separate ways. I did one over here and then instead drew it over here equal to. If you want, you can go right from here equal to f of b minus f of a all over b minus a. You can set it up as one giant equation. That's what I did differently on this slide than I did on the last slide. Last slide I worked it out previously and then set them equal later. You can, of course, start by setting it all equal and just having one equation if you'd like to do that. This one I think works really well for that because it's going to be 0 minus 0 and 2 minus a negative 1, which is going to be 0 at the end of the day on that side. And then, of course, we're just bringing down our quadratic. And now what do we get to do? We get to factor this one. I don't think so. I don't think so. I think it's quad formula again. Negative b plus minus square root b squared minus 4ac all over 2a. Negative 6 on the bottom, negative 2 out front. 3 squared is going to be 9 minus 4 times a times 2 squared is 4. And then we're going to have negative 3 times negative 4 is negative 12 times 2 more, which makes positive 24. And it's very similar to the problem that we did earlier because I kept everything the same. I just changed the sign in it. And we end up with almost the exact same roots that we dealt with earlier, right? We're going to get this down to negative 2 plus minus 2 root 7 all over negative 6. So I get negative 1 plus minus root 7 all over negative 3. Are we all okay with my work? Okay. Real quick here, just like we did before, there is two answers here. This is plus and minus. This is plus and minus, so we need to check both just to make sure they're in the interval in the first place. Because we don't have the exact same interval we started with. We have negative 1 to 2 here this time. So negative 1 and square root 7 divided by, so I get one answer here as 2.7429. That should work. And I'm going to get my other answer here. Oh, that's negative, sorry, negative 2.7249. And then we're going to have our other one here. No? Okay. Maybe Mr. Coppers typed things in wrong. This calculator don't want to work, right? Its negative sign don't want to work. So let's try it. 1. Okay. Negative 1 plus square root 7 divided by negative 6. I've got negative point.
It's negative 3 divided by negative 3.
That's it. Yep. Come on, Mr. Coppers. Let's do the problem right this time. Remember at the beginning of the year when I said you all were smarter than me and I just had more education than you? There we go. Negative 0.54, which is still in the interval after all. And then we have our negative 1 minus our square root 7 divided by negative 3, which gives us 1.21, which is also in our interval. So both answers here are good. Both answers here are good. Concerns here, questions here. Okay. Try this one out on your own. Try this next one out on your own. Given this function, determine whether or not we can use the mean value theorem and do it. I've done the last two. I'd like you guys to try this one on your own. We sure are a lively bunch on this live stream, huh? Hopefully they're just too busy taking notes and not asleep in their bed. Now there's an easy way and a hard way to do this problem. There absolutely is an easy way and a hard way to do this problem. Let's start working our way through this here. So, start with the basics. We need this to be continuous. Is it going to be continuous? Should be. What type of function are we dealing with at the end of the day here? It's a cubic function. Should be differentiable everywhere too, shouldn't it? Okay, so the theorem applies. So what did you want to do first to get this theorem out here? We got a couple of pieces of information we need to do first. What do we got to get? A and B, plug them in. Well, I got A and B, right? A is -1. B here is 1. What does that make f of A and f of B? What do we got? F of A is 0. Yep. What about f of B? -2. Okay. What else do we need? Yeah, we can do the slope. What else do we need? Before I'm going to do that, what else do I need? The derivative, okay? Now, let's use a little common sense here. Don't do this as a product rule. Don't do this as a product rule. Distribute that x through. Make this x cubed minus x squared minus 2x. Make it easy on yourself. Okay? That makes the derivative of f much easier to do. 3x squared minus 2x minus 2. Okay, you want to do this as two separate, you want to do the slope and then set this equal to that result, or do you want to do it all in one step like I did on the last one? Separate or together? Let's do a quick show of hands. Who wants to do it together? 2, 3. Okay, who wants to do them separate? 2. Jake don't seem like he cared, so together we're going to do it. 3x squared minus 2x minus 2 equal to our f of b, which is -2, minus our f of a, which is 0, all over b minus our a, which is -1. Okay, let's reduce. I've got -2 over 2, which is -1, correct? And on this side, I haven't done anything, 3x squared minus 2x minus 2. Okay, what are we going to do? Bring the 1 over, solve it like a normal quadratic. 3x squared minus 2x and minus 1 equals 0. Okay, now what? Factor this one. This one does factor. Mr. Kaufman is done torturing you for the time being. What does it factor into? What are our two groups here?
X minus 1 and 3x plus 1.
X minus 1, 3x plus 1. This gives us two zeros, x equal 1, and x equal negative 1/3. Okay? Are we all set here? Comfortable with the C values that we have?
So that's all we have to do for this problem.
It is. Now let's be careful here. Not both of these are actually usable answers. Because when we get to this part here, it is parentheses, not brackets anymore. So this one is not technically a viable answer. C is on the open interval. When we talk about C here, for this blue step, we're looking -1 to 1 with parentheses, not brackets anymore. So there, you need to be careful here. That's why I particularly singled out this problem for us to make sure we did. It has to be well within that interval. It can't be the endpoints when we get to this segment here. Okay? Concerns? Okay, let's do a word problem. Let's do a word problem. So here we have two stationary patrol cars equipped with radar guns that are 5 miles apart on a highway. I want you to know that this problem is inspired by Mr. Kaufman's original calculus teacher when I was literally your age. This is something that he did in a courtroom to try to get out of a speeding ticket. This is a real life example. So, he gets passed by a truck, the first patrol car. Speed is clocked at 55 miles per hour. 4 minutes later, the truck passes a second patrol car, and they clock their speed at 50 miles per hour. The truck must have exceeded, prove that the truck exceeded the speed limit of 55 during that 4 minute span. So, let's get started. By the way, this is how some police in counties actually do set up speed traps. How many of you guys have seen a cop and then like a little while down the road see another cop? Yeah, this is what they are doing. Because mathematically, you can prove that if you pass this point and then you know so much distance later, and at such and such time later, they catch you at this speed at this point, it means you had to have gone at least this fast somewhere between the two. So let's start by getting some things down here. So 4 minutes is 1/15 of an hour. Reason why we're doing 1/15 here is because we need to get units all on the same page, and we have speed in miles per hour, and we have time in minutes. So let's bring it all to miles per hour, because that's what we want to prove. Is we want to prove that the max speed between these two, or the min speed, or whatever the critical value is going to spit out here, is going to be somewhere over 55 miles per hour. So when I look at my 4 minutes, I'm going to convert that over to 1/15 of an hour. Are we all comfortable so far? Okay, so the function here, will it be continuous between 0, time 0, and time 1/15, 4 minutes later? Yeah, we're driving down the highway. You don't just stop on the highway. Unless something's wrong, you better not, because you're going to get into a car accident, or Mr. Kaufman's going to pull over and yell at you, because the highway's not for stopping, the highway is for driving. So we can safely assume that, yes, the function will be continuous between the two. Is the function going to be differentiable between the two? Well, for that, we would have to not have any huge spikes, right? So barring having to literally slam on the brakes to avoid an accident, we should expect this to be a nice, smooth, consistent curve. Whether it's accelerating or decelerating, we should expect a nice, smooth, consistent curve. The only time we should get a spike here is if we have to slam on the brakes to avoid a car accident. If we're slamming on the brakes, then we wouldn't probably be in this situation in the first place. So we can assume that this will be differentiable between the 2 points. We are making a little bit of assumptions here, admittedly, but it is a real world problem after all. So, theorem can be applied. The mean value theorem can be applied. We can find the average rate of change over this time frame, which the average rate of change is going to be a speed here, right? Position versus time. So, take what we have and let's plug it in. So let's talk about what we have here. This 1/15th, this is B. This is my endpoint. This is when our experiment is ending, yes? When is my experiment beginning? What time frame? 0, at time 0. In this case, we're not working X, we're working T for time, right? Okay, what is the F values here at A and B? Well, what do we clock them going originally at? 55. What do we clock them originally going at for B? 50. Okay, so you see how I have my information so far, right? Okay. Let's start by finding the slope here. Let's start by finding the slope here. So we're going to have f of B minus f of A all over B minus A. So this should be 50 minus 55 all over 1/15. Are we all okay with this? We're all set? So this gives us -5 divided by 1/15, which is what? -75. Now, of course, we're not going in reverse, right? The reason why it's negative is because from time 1 to time 2, it is lower. It is lower. So overall, we would expect there to be some drop because at time 1, we were going faster than time 2. But that still doesn't mean, it means that somewhere between the two, we averaged 75 miles per hour. It's only negative because time 2 was slower than time 1. If this was the other way around, and this was our A and this was our B, we wouldn't be having the negative. Which is normally how they actually get you. You pass the first cop, you think you're safe, you're good. So some people drive with a lead foot, myself maybe included. I like to go fast. So then you start going fast, and then you pass the next cop, and typically you're going faster. So it becomes even less work to prove because this goes from being -75 to +75, meaning your average rate between time 1 and time 2 was 75 miles an hour. Questions here? Concerns here? Okay. So that wraps it up for today. That wraps it up here for today. Here's our homework on the next one here. In the next section of 3.2, we're doing 1 to 19. We're doing the odd ones here, not every other, but each odd. So we are doing 1, 3, 5, 7, 9. I'd also like you to take a look at 25, 31, and the rest of those listed there. Now, those of us on live stream, I expect us to come in with 3-1 and 3-2 done. And you all here on Monday, you guys will be tuning in for the live stream for the first time. Don't be surprised if we spend the first couple of minutes talking about how this went for them and also what it was like for you guys. So maybe on Monday we might spend 5 or 10 minutes of the beginning of class looking for you guys to have some things in chat to say about how it's different at home versus being here. And likewise, I'm looking for them to come in on Monday with a little bit of feedback, something we'll talk about. So in the meantime, this wraps it up. So those of us on live stream, I'll see you all later. Hope we have a good weekend, and I'll see you all on Monday. And the rest of you, let's get started with our homework. Go ahead and end the stream there, DJ.